Hi fellow enthusiasts, welcome back to my channel. Let's go into today's video and we're going to come back at the end to wrap it up. Now you remember the video, the pictures you're seeing on your screen. It was the video we did last time on R433 megahertz transceiver. Now at the top of the screen you will see the transmitter, at the bottom you will see the receiver. We had promised that we would do an in-depth video or an in-depth analysis of how that video design came about. Now, the top one is made up of some blocks, likewise the bottom portion. But in the top one, we're going to concentrate on two blocks. Maybe there's a third block, but let's focus on two blocks. We're going to start drawing on that page you're looking at now. We're going to get a clean section and start drawing on it. So let's do that right now. So we're going to divide up the screen to demo the blocks. So I'm going to be drawing within this section. Right. So the first thing you notice is that transmitter there. Let me bring back that image. It's very important that we understand how the design was made. So the first thing you notice is that is a 433 module there, the data line, power line, and the ground. And then you notice also there is a microphone there in our own design in the modification we made. So this will be the audio section. So that's why I say there will be maybe three blocks, if you will. So let's use another color. Let's use this color and say that'll be um, so let's use a bigger marker. Let's use this one here. Okay. So if you divide this up this way and that way, I will explain each section, so don't worry about this. So the top piece, number one, let's use black. All right, number one here will be the transmitter. Number two here will be the amplitude shift key or ASK, and number three will be the audio modulation. We are very familiar with the audio modulation. We're very familiar with the transmitter, and probably some of you are familiar with the amplitude shift key, or in our own case, we call it transistor switch. So there's a particular transistor here that function as a switch, and the other transistor that function as the in conjunction with the transmitter. Now, this is going to look a little bit ugly, but we're going to draw it clean later. So this transistor here, let's use red to highlight it. This transistor here is working in conjunction with the oscillator, crystal oscillator, and other inductors and capacitors to provide the function of a transmitter. Then the other transistor, let's try a different color. The other transistor, which is this one here, function as a transistor switch, and that transistor in conjunction with the resistor here function as a switch, and these two combination give us what we call the amplitude shift keying. So let's go to that box that we're trying to create and redraw the circuit diagram here. Now you are familiar with different types of AM transmitters and FM transmitters, some in our channels. Please, if you don't know how to build this, check out our channel. You will see lots and lots of transmitters. Let's just draw a quick and dirty one right now. So we have a transistor, and normally in our simplest transmitters, we have a capacitor this way, we have a resistor this way, and this resistor goes to ground. We have an inductor and another capacitor here, variable capacitor, and these two will form our tank circuit. There at the base we have a biasing resistor. Normally we use 2K2 for most of our designs, and then down here we have a capacitor, and you can just connect your antenna somewhere here. the value of this capacitor is dependent on the frequency, because you want to match your antenna to the frequency that you the frequency of interest. So this is the way we normally do it. So this will be the power supply positive, and then the ground down there. Now, if you build this, the thing is, this transmitter is always going to be transmitting as long as there's power, right? But the R433 was designed for intermittent use, so the battery can last much longer. So to be able to do what they did, instead of connecting these portions to ground, they connected that through another block. So this will represent number one in our block, and then the number two is a very simplistic one. So let's just go and do that right now. Again, I want to keep this brief, so let's erase large. Let's remove everything. Okay, I want to remove strokes. I can strokes erase. Okay, let's do that. Right. And then let's erase large. So I'm going to remove this portion. Let's do strokes again. Strokes erase, because we want to remove this line. Okay, good. Now, what I want to do now is to design the second piece, which is the amplitude shift key. And it's so simple. What they did was, you have a transistor functioning as a transistor switch. So that transistor is here, and that ground, so these two, instead of going to ground, is connected to the collector of that transistor, and then there's a resistor here. There's a biasing resistor, and then this goes to ground. So this will be our block number 2. So when you send your signals here, ones and zeros, 1 and 0, when you send a 1, this transistor will switch on, this particular transistor. So let's call this Q1, then this will be Q2. When there's a positive going pulse on the base of Q2, Q2 will close and effectively grounding this resistor. So we'll call this RE, and let's call this C1 for now. So this transistor will ground C1 and RE, effectively turning on the transmitter, and it will send out a burst of RF signal. Now, there is no audio connected to it, so what you will just see is, on the receiving side, tuned to this frequency, to this resonant circuit, it will receive a burst of amplitude signal from 0 to something, and then it will go away depending on the bandwidth, depending on the pulse width of this signal that is sent. And that is what generates the signal on the transmitters on the receiver side to say a 1 has been sent. When you send a 0, there's nothing received on the receiver side, because 0 will not turn on this transistor Q2, and if Q2 is not turned on, then there's no signal coming out from Q1. So this is basically your amplitude shift keying. Amplitude shift keying means you're sending signals that are changing in amplitude only. So it goes from 0 value to whatever value the transmitter is able to output. All right, so based on sensitivity of the receiver as well. This is it basically. The third block, which we're just going to talk about quickly, the third block is the audio circuit, or the audio modulation, which in our case, it was a very simplistic one. We had a condenser microphone, so grounded, and then you just have the normal biasing, a resistor going to the positive side, and then a capacitor coming from here, then going to the base of the transistor. So this is the positive as well. So this is basically it. We have our third block right here. So the first block is the, so let me just call this 3. All right, so let's go through and recap. Let's get a different color of highlighter. So our first block is here, the transmitter itself. The transmitter is our first block. Our second block is the amplitude shift key. And our third block is the audio transmitter, the audio mixer, or the condenser microphone mixer. This is it. Very simplistic. I'm gonna redraw that because if you remember our theory on how to draw good circuit, a resistor cannot be just drawn anyhow. There must be a particular order. Yeah, the arrow when the zigzag is coming from the left, from the right, it will end on the left. If it's coming from the left, it will end on the right. So if I had drawn it this way, then I must end it from the right. But if I had drawn it this way, then I must end it on the left. So the origin must be respected, right? Anyways, so this is it. This is the transmitter. So in the second video, we're gonna give you the receiver circuit, how it was designed originally, and how we're able to modify that to receive a clear audio. Because there's an intention behind that design. They built it for a particular purpose, to recreate. Remember, on the transmitter side, you're controlling the transmitter by sending a 1 and a 0. But the transmitter doesn't send a 1 and a 0 per se over the air. It sends a burst of RF signal, which is just, if you will, if it's a pure sine wave, it will look like sine wave. But it's not really a pure sine wave. So you get a burst that could be in any shape. Let's try to create that shape a little bit. So it could be something like this. So this, I am assuming that this is already modulated with an audio signal. Otherwise, the amplitude will be uniform. If there was no audio signal, the amplitude will be uniform. So it will be similar to a sine wave, but more compact depending on the frequency. Right? I'm just giving it one cycle here, but it could be something similar here. Let's just small erase. Small erase. Let's take this portion out a little bit. All right. So when this signal is then received on the receiver side, the receiver, one of the tasks of the receiver, apart from accepting or intercepting the signal, is to interpret it and reproduce the original signal, which is a 1. So the receiver, part of the task of the receiver is to convert this sinusoidal wave into a pulse, a digital pulse, which will be a 1, and then it will stay silent for as long as there's no other signal coming. And if you were able to hold the switch down, or if you send a signal that is very long pulse width, then what you will receive will represent that pulse width. So you receive something like, it will go from 0 to 1 and then stay on until the signal disappears. So how do we recreate this? That will be the subject of the next video that is going to come up shortly. Now, but let's just go back and analyze this, or talk about this one more time. So we have our R433 transmitter, and it is 433 because it has a fixed frequency. Fixed frequency, the crystal is 433 megahertz or 315 megahertz. So in that case, you are not using this inductor and a capacitor to create a tank circuit. You're using a fixed inductor. In such cases, you will have you're using a fixed capacity, fixed frequency, sorry. So in such cases, you can have a crystal connected to this circuit. Now you can convert the circuit you're looking at here um, to a crystal transmitter by simply connecting the crystal across this. So in that case, we're going to remove. So I'm going to just do a rough work here. So I'm going to cross out this capacitor, and I can, in place of that, connect a crystal to the base of this circuit. This is not a very clear design. Look at our circuit diagrams to see how to design a very good crystal transmitter. but this is just a crude representation. So if this is a fixed frequency, then anytime you power it on, the frequency will be the same. This is important for remote control devices, because if you use the original circuit we have here with inductor and a capacitor, it has a variable frequency that is dependent on voltage. So it's called voltage controlled oscillator. When you use voltage controlled oscillator, as the battery power degrades or reduces, the frequency changes, even if it's slight, but it will still change, right? So if you want to have a fixed frequency for a remote operations, you want a fixed frequency transmitter, or you have to have a fixed voltage transmitter. Make sure that voltage is stable, and the proximity of any object to the antenna or to the circuit is the same all the time, because if it changes, it could affect the waveform or the wave pattern. But with a fixed frequency transmitter or a crystal oscillator, you are guaranteed the same frequency over time, as long as the battery is strong enough to bias the transistor and other associated components. You are guaranteed a stable frequency up to 99 point something percent, more than 99% stable frequency. Voltage control oscillators are not great as remote control devices. And in that case, you must ensure your battery is regulated, proximity to antenna, all the circuits, all the RF circuits are maintained the same or constant at all time. That is difficult to do. So for us, we recommend that you use a crystal for this. What we demonstrated here, to recap one more time, is the three boxes required for an amplitude shift keying remote control based devices. The one box is the transmitter, and our recommendation is to use a crystal oscillator. The second piece is the amplitude shift keying. For amplitude shift keying, it's just going to be a simple transistor. If you're going to turn this on with, so let me use a different color. If you're going to control this with a positive going signal, we recommend you use an NPN transistor. So there's going to be a resistor here, and then the signal goes here. And this goes to ground. So the ground from the crystal goes through the transistor. If for any reason you want to use a negative going signal to control this, then you might consider using a PNP transistor. A PNP transistor is enabled or turned on using a negative going signal. So in that case, let's change back to red. Use your transmitter. Still crystal, we recommend that. But on your amplitude shift keying, we recommend using a PNP transistor. PNP transistor, much similar to NPN transistor. However, in that case, your signal, the signal that controls or biases your transistor, is going to be negative going. So in that case, the emitter goes to positive, and so this should be grounded as usual. So it should be drawn upside down. So let's draw this upside down to represent the actual. So let's do light strokes. Light strokes. Erase strokes. So in this case, I'm gonna go. My transmitter is gonna be here. TX T crystal goes to ground. However, the amplitude shift keying is gonna be now a PNP transistor. I'm gonna put the arrow on the top here. This will go to positive, and then my resistor will still be here, part of this, and then my collector will be here, and then this will be controlled by a negative going signal. All right, so when this negative going, the transistor will switch on, sending power to the transmitter, and then the transmitter will do its job of sending out pulse. If I'm using an NPN transistor, this will be PNP transistor, this will be NPN transistor. When I'm using an NPN transistor, I want to use a positive going pulse for my data line. The positive going pulse will turn this transistor on, and then this transistor will ground the whole transmitter circuit. In that case, my positive power supply will be from the transmitter side. So everything will be grounded, and then the signal, is burst of signal will be sent. If I want to use a negative going signal to control the system, then I have to have a PNP transistor, and then that PNP transistor is turned on by a negative going signal. In that case, the positive again will be grounded, will be shut up. The emitter will be shut to the collector and sending power to the transmitter, and the transmitter will do the burst. Now, if you already have your R433 and you want to use it as is, but you still want to use negative going signal to control it, or yeah, so you have to connect another transistor in series. So in that case, what you will do is, for your pulse, you just have to have a signal conversion. That's just what it is. Use a signal conversion. So you know that the original block diagram will be the TX, which is crystal based. I'm giving you block diagrams here because I want to teach you the principles. If you need the actual circuit diagram, go to our channel and get a circuit diagram of your choice. We have so many circuits on transistors. Transistors are switches. We have transmitters, different transmitters, one transistor transmitters, lots and lots of transmitters. We even had a transmitter based on 555 timer for amplitude modulation. But I'm just giving you general block diagrams because this is how I was able to build up my repertoire of designing circuits. When you understand the block diagrams that are required to build whatever you want to build, when you understand that, then you don't have to be a slave, in quotes, of a particular circuit diagram. When you understand the theory, you can go ahead and create anything you want to create. So in this case, I'm just going to use an example of the regular, I will call it regular, R443 transmitter. R433, sorry, R433. So this will be the normal thing you will have, and here you have your amplitude shift key in the ASK. Amplitude, of course, because of the signal goes from 0 to a particular value. There's no audio modulation on the original design, so you can't call it amplitude modulation or frequency modulation. You just amplitude shift key, shifting the amplitude from 0 to something and then down to 0. That's what you're doing. Now, this is the normal way it is designed. So this goes to ground, but then you have a signal that goes into the ASK that is positive going signal controlling your ASK. What I'm saying is, if you have this circuit as is and you still want to build, you want to use a negative going signal to control it, because apparently only positive going signals will send something out. If you have a negative, if you want to show when something is interrupted and you don't want to keep your transmitter always on, the idea is to conserve power. You want to only control this when the condition changes to negative. Let's say there's a light source. Let's say there's a something that always produces a signal, but you want that when the signal is out, you want to transmit or send a warning. Then you want to use maybe an optocoupler or maybe a PNP opto transistor to control the signal, so that when the signal is removed, it goes negative, and then you turn on the transmitter, so you save power from the transmitter. So what I'm going to recommend you do is, let's just delete this. All right, so what I'm going to recommend here is you connect a PNP transistor here, and then your signal goes in through the base of this transistor. Remember, it has to be negative going signal. So this negative going signal, you want it to shut down. You want it to shut this way. You want this to happen. So this goes to ground. This portion that will go to ground, the collector, that should go to ground, you connect a resistor there before it goes to ground. And then this resistor will be high value. I would say like 10K or above. So let me just say 10K for now. And then the emitter goes to positive. What happens is when you send a low going signal to the base, the emitter will connect to the collector, sending the power supply to the collector, and then the collector is connected to the base of the transistor of the ASK, and then that ASK turns on and controls your remote device. And then this 110K resistor is just there to limit the current flow, or to provide like almost like a voltage divider. So the transistor and the resistor, and in this case you can call this resistor your RL, or the load resistor. But what happens is that the voltage that is at the emitter will be made available at the collector, and then that voltage is used to control your ASK. So this is how to convert the existing 433 to use negative going signal. So this here doesn't even have to be a signal. So I'm just going to circle it. I won't delete it. I'm just going to circle. This doesn't have to be a signal. And I'm going to put another circle. This could just be an up to. Okay, this is not bold enough. Let's make it big. Yeah. You can use an optocoupler, a PNP photo transistor, such that the amount of light can, when the light falls or light condition changes, the luminous intensity changes or whatever, when that happens, then the signal is connected to your ASK. Your ASK controls your transmitter sends you a pulse to tell you, hey, the light has been blocked, or signal has been removed, or whatever is the case. But the way the R433 was designed was for a positive going signal. All right, if you want to do negative going, now you know what to do. Okay, so I'm going to stop this broadcast right now. In the next video, I will show you the receiver section, the receiver circuit, how it is designed, and what we can do to improve the signal. And then in the third video, maybe in another episode, not today, but in our last episode, we're going to build this out and demonstrate to you, because we're going to make a modification on the circuit. We don't want to build it from scratch. We'll take one of the receivers that we have and modify it to demonstrate what we are giving you the theories of. All right, so thank you for joining this broadcast right now. Remember to like, share, subscribe, comment, and until we come your way again with more contents, stay enthused.